On this slide, we will discuss the behavior of gases as a function of temperature. And this behavior is described by Charles' law. The law states that the volume of a gas increases directly and linearly with respect to temperature on centigrade scale for a constant mass and at a constant pressure of the gas. This law was introduced by Gay-Lussac, a person that is a very honest and good gentleman who gave credit to Charles, but Charles never published this material, but preceded Gay-Lussac by 15 years or so of observation. Now, nevertheless, the law can be written mathematically and also graphically the following format. If we were to take a specific amount of gas at a particular pressure and raise its temperature, its volume increases linearly. Now we are measuring temperature in degrees centigrade as far as this experiment is concerned. And so the linear plot shown on the right hand side, the blue line, can be described using equation y equals to mx plus c, where y is the volume V, the intercept c is a, and the slope m is b. T is on the x-axis variable. And we have to keep in mind that pressure and mass are being kept constant under these conditions. So we can describe this linear behavior in an alternative way that is actually more interesting. And that is to relate this expression to the absolute scale of temperature and also to define the lowest temperature one could possibly achieve. So we rewrite this linear expression as V equals to V0 plus the partial derivative of volume with respect to temperature, constant pressure, multiplied by T, where the V0 is your intercept on the volume axis when the temperature is dropped to 0 degrees centigrade. The slope of this blue line is dou V by dou Tp, or the variance of volume with respect to temperature, rate of change of volume with respect to temperature at constant pressure. We have a special meaning for this, rate of change of volume with respect to temperature, and that is illustrated in terms of a constant, and this constant is defined and observed to be the same for all gases irrespective of their chemical composition. In the bottom here on the right side is shown animation, actually a snapshot of the animation, similar to what we have seen in Boyle's law. You have a gas sample embedded in a cylinder with a piston, and the temperature of the sample is maintained by the blue bath, which is either heated or cooled as desired. And the temperature gauge and the pressure gauge monitor the properties of the gas sample enclosed within this. Now we keep the mass constant, and we also will keep the pressure constant. So the piston would apply the same amount of pressure onto the gas sample. Say it is open to the atmospheric pressure or any other desired pressure. And so the pressure gauge should read the same. So now we allow the volume to change, and we raise the temperature. So when we raise the temperature, the x-axis values are increasing, and the experimental observation has been that the volume of the gas increases. So this is shown in the animation and at this Wikipedia website. And after you have watched the animation, you should be able to complete this graph on the right side. V versus T, and in fact this should can be a capital T where it is absolute scale of temperature, which we're going to define very soon, or it could be the centigrade scale. The values on the x-axis will differ based on what scale you choose. And as you monitor the animation, pay attention to the pressure and the temperature gauges here. Now, the we want to think about what would happen if the temperature is so adjusted that the B times T equals to minus A. That is, when since B and A are constants, we can pick a temperature T such that BT equals to minus A. Now think about what would happen if under these conditions at this temperature, and what will be the consequence of it. What will be the value of T then? So this is an important question which leads us to think about the next slide. And before we move on to the next slide, I'd like to make sure that we complete this graph V versus T on the right hand side.